Hi everyone, my name is Aimee Sutton. I work for Imperas Software. I'm here to tell you about our Imperas-DV product, RISC-V processor design verification solutions. Okay, so as RISC-V adoption began to grow, Imperas recognized early that design verification was going to be a challenge in this new world of custom CPUs. A new group of processor developers was emerging. Organizations who in the past had purchased pre-verified processor IP were now developing their own, and some were undertaking CPU verification for the first time, and quickly realizing that existing techniques for DV were useful but insufficient for RISC-V processors. Imperas created our Imperas-DV product to fill this gap. Our goal with Imperas-DV is to make it easy to build a comprehensive, reusable RISC-V processor verification environment. Our product offering includes our verification IP that encapsulates a reference model of the target processor, functional coverage code, directed test suites, and a software debugger. Imperas' fast processor models support the full RISC-V ISA and are architected to enable customization. Imperas-DV works with all verification environments, whether they are implemented in SystemVerilog, C, C++, or Python. It supports increasing usage from early bring-up to constrained random stimulus for verification closure, and it's based on the RVVI interface, which promotes best practices and reuse in verification. Imperas-DV is in use today by many organizations, some of which have already reached silicon. So before I go into how Imperas-DV works, I'm going to briefly explain the RISC-V verification interface, or RVVI. RVVI is an effort to standardize the communication between the RISC-V processor test bench by identifying interfaces that are common to all RISC-V processor test benches. And the diagram being presented illustrates this architecture, and the common interfaces are shown in yellow. These include RVVI trace, which is a specification for the interface between the processor under test and the test bench. It identifies the information that the test bench needs in order to verify the processor's correct operation. Another interface is RVVI API, and this is the specific set of functions that a test bench component or verification IP should implement in order to comprehensively verify the correct functionality of the processor. And implementing these functions requires an instruction-accurate model of the processor. The third interface is called RVVI VVP, or Virtual Verification Peripherals. This is another standard set of functions allowing for control of memory-mapped peripherals from the program running on the processor. RVVI has been a collaborative effort between Imperas and commercial and open source organizations. It's an open standard with the source code available on GitHub. The RVVI standard has enabled the development of RISC-V processor verification IP, such as Imperas-DV. And let me tell you how it works. Imperas-DV is instantiated in the customer's test bench and connected using the RVVI trace interface. The same program is run on both the device under test and a reference model of the target processor. As each instruction retires, the internal state of the two is continuously compared. Mismatches are reported immediately, meaning there are no wasted simulation cycles running past the point of the first error. This is in contrast to other methodologies like post-simulation trace compare or signature compare, where you have to wait until the program completes to find out if the test has passed or failed. Imperas-DV uses a proprietary pipeline synchronization algorithm. Sorry if this sounds funny. It's okay. In order to respond to asynchronous events. These are events that occur asynchronous to the execution of the program running on the core, such as external interrupts or halt requests. And these are a frequent source of bugs in RISC-V processor RTL. Because of that, it's important to have a solution to verify them. It's a critical part of a complete verification strategy. And we'll see more about how Imperas-DV handles these events in the next slide. So the waveform shown here depicts a scenario where the processor has 8 external interrupts, and each is being asserted on subsequent clock cycles in the space between 2 instruction retirements. It's an extreme example, but it is a valid case. As an architectural model, there's no way for Imperas DV to predict precisely which interrupt will be taken and when. However, using our pipeline synchronization technology, we can analyze we can analyze the processor's response to these net changes and verify that it is legal. If not, an error is flagged immediately, and debug information describing the set of legal scenarios is provided to the user. And verifying the correct processor behavior in the presence of these asynchronous events is a difficult problem to solve, and we're proud of the solution we have with Imperas DV. It's part of what really sets our products apart. So sometimes it can be helpful to debug from the software perspective, even while running an RTL simulation. The user might want to set breakpoints in the test program or inspect the internal state of the reference model, while also having access to their waveform and RTL debug environment. This is possible using the Imperas MPD eGUI debugger. It provides a full-featured software debug environment, and it allows for alternating control of the simulation between it and an RTL debug tool. In this picture, it's SystemVerilog, but we can do this with any commercial EDA simulator. Now, another facet of Imperas' processor DV solution is RISC-V ISACOV. This is functional coverage for the RISC-V ISA. Here's the problem that it addresses. There are a number of instructions associated with each RISC-V extension, and each of those instructions requires coverage of operands, registers, not to mention data hazards, cross-coverage with other instructions. A large amount of SystemVerilog code is required to implement the coverage model, but writing it by hand would be really time-consuming and error-prone. So the solution that Imperas has come up with is to use a machine-readable definition of the ISA as the input to a coverage generator. The output of the generator is a modular set of cover groups that can be selected based on the extensions implemented by the target processor. And since this coverage model is defined by the RISC-V specification, it's completely reusable between projects. The coverage model is used in the RVVI reference test bench, and it's sampled with data from the RVVI trace interface. It's also designed to be extensible by the user. Okay. Imperas RISC-V ISACOV is delivered as SystemVerilog source code, and it requires a SystemVerilog simulator to collect, merge, and display the coverage results. And the image on the right shows ISACOV data being displayed in the SynopsysVerdi tool. However, it can be used with any simulator that supports the SystemVerilog standard. The coverage code has been architected to be extendable by the user, making it easy to add coverage of custom behavior or microarchitectural implementation. And the last thing I'll mention about RISC-V ISACOV is that it's delivered with detailed documentation in both Markdown and CSV formats. The documentation is designed to be readable by both humans and machines so that it can be imported into a verification plan, whether that plan is created in a spreadsheet or using a verification planning tool like Cadence vManager. Now let's talk briefly about test stimuli. So test stimuli for processor verification generally falls into 2 categories. The first is random tests. These are programs created by a random instruction stream generator. There are commercial and open source solutions for ISGs available. However, Imperas does not yet have a product in this area. The second category are directed tests. These are test programs written to target a specific set of features or functionality. Here, Imperas provides architectural compliance level tests that are freely available to download. In addition, we've developed a directed test suite for the RISC-V vector extension and for MMU and PMP functionality. The test suites are configured and generated based on the customer's requirements, and they're delivered with detailed coverage information. So in summary, Imperas design verification products provide a full-featured RISC-V processor verification solution, which will give your team a significant head start in verifying your custom CPU. And to hear about one user's experience with Imperas DV, please attend the upcoming talk called Challenges in CPU DV, Why It Boots Linux is Not Verification. That's happening today at 2:15 p.m. in the theater upstairs. And please feel free to chat with me after if you have any questions. Thank you.